Nice to see you fresh after the coffee break. Probably you got some energy for Casino Drive. So the story of our team, that's what we will talk in next 45 minutes. I am Oleg Kharchenko, a newbie Scala developer at Amazing Gaming. Newbie, that's because I'm only doing Scala on daily basis for last 12 months probably, which is quite not that much comparing to Java experience. Right here you can see the link to GitHub repository and the QR code. There are links to the application that we will investigate. It's deployed on Heroku. You can even load it on your mobile device if you want. It's not that pretty neat mobile design, but still it works on my mobile anyway. So the plan, we will go through the problem that we faced. Then we will check the technology options, and then proceed with the prototype design. I claim this talk to be of intermediate level, which means we won't stop on the very basics like actor mailbox or something. But on the other hand, there will be no scary monadic constructions. So just the regular code that you see on your daily work. So please raise your hands, those who can explain the difference between command and event in CQRS. Just to know. Okay, nice. And keep your hand raised, those who have written at least 100 lines of code in Akka. Oh, great. And who have production application running on Akka? Oh, this looks scary. Probably you will need to teach me how to do things. Okay, then we will proceed with the questions at the end. So the casino crash course, just so everybody on the same page. When we're talking about the game in casino, we're obviously talking about the game of chances like roulette, baccarat. We have bets and win. You place in a bet and hope to get a win, which is much bigger than bet, but there is risk that you will lose your bet. We will talk about spin and game round. Spin is just a single act of gameplay, just explicit action of a player, and game round, it's most often consists of just one spin. Just for sake of demo, we will take this simple definition. The story started several years ago. Let it be the dinosaurs era of the evolution with one of our core products, Casino. It is much more complicated than that. It's kind of, you know, this big ball of mud that everybody is talking about in these school microservices meetings. But we will mainly focus on the intercommunication of three main components. Let's call them the client, game, and wallet. But instead of 1,000 words, let's just feel the spirit of Casino. And take our chances. This is how real roulette look like. So we can try to place a bet. Here you can see the bet amount and your current balance. And if you run a spin, here spin is literally spinning of the wheel. Yeah, hooray! Good signs. A little disclaimer, we are not running illegal casino, no need to call to police. Come on. So we will mainly discuss the intercommunication of three main components that you see on the diagram. That's a Flash client, game engine, and the wallet. And as you can see, these two are deployed on the same Tomcat server, and the communication between these two components is just local JVM communication, while communication to the client is HTTP. Back in the old days, it was XML and Flash client, but it's evolution story, so nowadays it's JavaScript apps. And so let's check the flow. It is what the heck? It is almost a textbook example. There are two phases. The first one is game launch, just mainly for understanding. There is a session that you pass as the parameter to the game link, and then game engine can fetch the information about this particular player, his balance, and the gameplay itself, it's quite simple. It consists of several main phases. You can think of it as a just real-life, real land-based casino dealer that first collects the chips, then spinning the wheel, and then check which bets have won, which have lost, and distributing the bets, the winning chips back to the players who have won. Obviously, those who haven't won, they get a win of 0. And this whole thing is a transactional action back in that days. Which means if something goes wrong, everything is rolled back to the very beginning, and everybody thinks that nothing have happened. So let's actually check a real-life code snippet that was doing it. It's quite easy. It represents all the steps that we have seen on the diagram. First, it checks the bet if it's correct or it's not. You know, in the roulette there are 36 pockets, so 37th pocket is incorrect, obviously. Then there is an action of placing a bet. What's happened under the hood here is everything that is so familiar to any Java developer. It's a whole bunch of DAOs and SQL database calls. So as a result, there are essentially two database calls which produce a record of a transaction and update in a player database where player's balance is stored. What is done next is, this is essentially the invocation of a random number generator, wheel next pocket. And then the result is calculated from the win is calculated from the result, depending on the bets that you placed. Here we can see some ugly mutable state that's mutated with the results. They are sticked right away inside this mutable object. What's happened next is pretty much the same as was done during the bet. It's payout, again, one record for the transaction, and update in the player database. And as the result, save state. What is done here is the whole game state is saved into the database as a big snapshot, just all the results, the winning pocket, the result in balance, all the stuff saved to the database as a great big blob. And the business requirements, they always come unexpected, pretty much like this meteorite here, which is going to hit this transactional there and pretty much cause the Big Bang, which will cause the extinction of all the dinosaurs, as we will see. What we have after the Big Bang, it's actually, the business requirement was that the client would like to place our games on his website, but he would like to store the player's balance inside his database, which pretty common for the industry. It was just our time to realize how it works. And what we can see after the Big Bang is that it's all pretty much the same, except for the two components are now deployed on different nodes, and the communication is done over HTTP now. We have two databases, and there is no chance to arrange transactional handling of this whole step. I'm not considering two-phase commit as a real option, of course. this way or that way, if you probably you are all facing microservices movement, and this or that way you can end up in exactly the same situation if you split in your big ball of mud into several microservices. You can face the same situation when you will have two separate databases instead of one, and you somehow need to handle transactions. And whenever, if you're interested into the patterns, you have probably heard of some kind of saga pattern variations. So this is something that we will implement. So let's think what can go wrong now when we have a wallet module remote compared to the game engine. Obviously, we have now unreliable network between game engine and wallet. There can be read timeouts. So, for example, in this situation, we will probably have to repeat a bad transaction once again until we get the successful result. So, after the Big Bang, of course, as it was in the history of the Earth, there was nuclear winter. And it was dark ages for us because we started, after this move, we started to face a whole bunch of new problems since we removed the transactional, and now systems started to end up in some inconsistent states. Whole bunch of new problems, game rounds left open, players get unsatisfied. Some wins haven't ended up their players. They angry, they complaining. Of course, the remote wallet cannot be that fast as the local one, and we had to apply some various kinds of performance optimization. The most ugly are like caching the player's balance, which is as ugly as it seems. We try to apply various kinds of queues, and almost all the attempts were quite pathetic. And as we added each new crutch to the code base, we realized that technical debt is increasing, and we have to somehow handle the situation in a better way. So, again, as it was with the Earth's evolution, the nuclear winter allowed appearance of new, more intelligent creatures. I'm talking about the frameworks for CQRS and for actor model. There are obviously many implementations out there. We have evaluated a couple of them. Like Eventuate, for example, but frankly speaking, Akka was the love from the first sight. Since the moment when we encountered it on the Coursera reactive programming course, it seemed to have all the components that we needed for the fast and reliable spins. In spin, this small move, small action, little click is the essence of the gaming business. If player get delay for a second, he get bored in a blink of an eye. You keep replying slowly for 10 minutes, and player will just leave. That's the reality that we face. So that's the key to success. And the second part is the trust. You have to need convincing arguments when you're talking to an angry player which believes that you cheat somehow, and you don't want to pay him his win. So you'd better have some records and arguments when talking to him. And I guess in this respect, audit, which is always mentioned among the benefits of CQRS, is quite underestimated. As a natural consequence of the audit benefit, there is reproducibility. What we found very, very productive is that nowadays, when we see an exception on production environment, what we are doing, we just take the whole bunch of the events of a player and copy-paste them even to your local environment, and voila, you have a reproduced scenario out of the box. You don't need to to dig tons of log files, it is much more convenient. So let's now try to solve somehow this problem, right? Let's try to create a prototype of a game that is free of this limitation, and let's think. We now at the point that we were a couple of years ago. We now realized that there is something wrong with good old synchronous Java model. We have gut feeling that Akka is the right tool. So let's try to use it. Back when we started, these are actually the technologies that we are using on production, just not all of them, but the points I would like to stop is that it seems so obvious to use Play framework for everybody in Scala community, but when you're moving from Java, you may still have some hesitations, and we did try to stick Akka into the Spring Boot. Hopefully you will not do that. We did try to use Akka HTTP as a replacement for Play framework, like lightweight replacement, but still we ended up with the Play framework. Now the solution for event journaling. Back when we started exactly a year ago, we were in this room and asking people's what solutions do they use, and mainly they were asking, like, we using Cassandra? Well, because everybody is using it. And it was not very convincing, but after all, we did adopted Cassandra as well, because it's optimized for writing, it seems a good fit for CQRS, it's homogeneous topology, and it's very convenient for us, because our load is naturally scaled by player. You have more players, you have bigger load. The serialization, we actually started, we had some hesitations when we started with new technology, so we started with JSON just to see messages in bare eyes. But after that, we decided to leave it as is and not to use protobuf or Kiro, because we, on one hand, we don't have that heavy requirement for productivity, but on the other hand, we have a whole bunch of investigations, and sometimes it's just easier to go right away to the database and then see the result right away. So let's, when you're doing an application, you probably start with a user requirements, then proceed with the user interface, and then go down to backend. Let's try to implement a simple game, like the most simple that comes to my mind is coin flipping. You have already seen how roulette works, so let's try to implement something like this, but in a right way. So let's create clickable zones for placing a bet for two options. It's fair coin. There are no edge outcome here. And we can flip a coin with a head, with a bet on a head. And let's see the result. The outcome was head, so our win is 3-2. The game pays like twice of your bet, which is quite fair if you flip in the coin. The resultant balance is 13, and win was twice the bet, the 6. That's just regular requirements that you would need when you create in a game. There is also click to continue, this yellow zone to proceed with the game once you understood the outcome and you figured out if you have won or you didn't. On the status bar, obviously, we would like to have some hint what game is expecting from us to be clear. And now it says the game is finished and it wants us to continue. That's WebSocket default WebSocket timeout on plate 2.6. So if we continue, we start with a new round. The first one was 0, now it's 1. And we can play further. There can be some exceptional situations that we will handle as well. Let's take a player that have only balance of 2, and we're trying to place a bet of 3, and we have no enough credits. And now let's think. How would we like our game to behave in case if something goes wrong. So I added some simulation of an errors in communication between game engine and wallet, and when we're trying to place a bet, something can go wrong. Not this time. Okay. So we want, for trust's sake, we would like to provide player as much information as possible. We are not responsible for the wallet module anymore. And we don't want the third-party service to screw up the impression about our product. That's why we need to provide to keep player ensured that we are doing everything to make his win being processed and just to avoid the situation when he starts to go and start playing to help desk and provide bunch of support tickets. So we can say that we keep trying to process the bet. Currently, it is attempt number 0. In 10 seconds, we will try again and again and again until the service go up. We are not responsible for the service anymore. It may go down for maintenance, and it can take significant amount of time. So we may need many attempts until we get a successful result. Of course, everything goes well under the blue skies, but when something goes wrong, we need to handle it decently. One more requirement, obviously, is that we would like our game to get restored to the very point where player had left it, in case if he closed the browser or moved to another device. So if we start again, we are again on our second round and exactly in the same situation because we haven't confirmed the win. When doing an event-driven system, you will probably start with coming up with a domain events of the system. You can employ some DDD techniques like event storming. You can come up with some ad hoc design, but this or that way you will probably have to reason about the system in terms of the domain events. What domain events do we have? So the very first step is placing a bet, and let's call it bet accepted. This is merely the fact that player was trying to place a bet into our system. Of course, you would like to store this very fact to the persistent storage, because you would look miserably in case if something went wrong, a player is complaining, and you don't even have an idea if he even tried to place a bet. You can check your logs, but there is nothing in your database. What personally for me was helpful is when I was, so to say, refactoring this code to event-driven approach. I was thinking about small checkpoints inside the original code, and so in case if something went wrong in the middle of the processing of some method, I'm thinking about the place where I will start from in case I will get recovered after the system goes up again. So these are small checkpoints, and if something goes wrong, in worst case, I will start from this point and will go further with more retries. The second fact that you will clearly would like to memorize is the confirmation from the wallet, because it's an outside system from now on. Then, when we get confirmation, we can go ahead and run the wheel. And once we get the result from the wheel, again, we would like to store it into our persistent storage. Again, because you clearly don't want to change your mind regarding if player have won or he didn't. You only want to notify player about the result after this store it into some persistent storage. And the same goes about the win, which is the last step here. And after that, we have already all the actions stored already in these events, and there is no more need to store the whole snapshot. We have all the steps already recorded. The catch block covers the failures and errors cases when communicating with the wallet. We will distinguish client-side errors and server-side client errors of HTTP protocol and server errors of HTTP protocol. So in event-driven system, each particular event switch updates the state, and we can factor out 5 main states in this particular example. We start with waiting for a bet, then action of a player to start the game switches to collecting, where we're expecting for confirmation from the wallet, which will allow us to proceed further. Then we do calculating of the results and proceed to paying out. Again, after confirmation, we end up in a finish state. And here we're waiting for players click to the clickable zone to continue. And then goes and game starts over. Now let's think about how to implement the communication between backend and the client side. As a JavaScript developer, I would probably love to have just notifications from the backend in a synchronous manner and let underlying technologies like React, Redux, or in our case, thanks to my colleague Artem, it is React plus RxJS. The most obvious idea that comes to mind when we decide to arrange this kind of notification is, why wouldn't we just send all the domain events directly to our user interface? By definition, these events have all the updates that we need. So we arrange in some kind of replication of a state inside the backend, and in order to have user interface in sync with the game state inside your backend server. And in UML, these are incoming messages, these are outgoing, and in purple, these are communication with the client, and these are in gray communication with the wallet. So you're expecting for a flip command, and once it's done, you sending back the notification that the user interface should get updated with the current bet. Same again, we're sending back the result, the outcome of the result, the outcome of the game. And we, with each response, we also have the current resultant balance that we send in again to the user interface in order to have it in sync. And finally, we're expecting for the user interface sending us the click to continue command, which starts new round. And once it started, we get back to the bets awaiting state. So let's let's try to check how it works. Okay, no communication yet. We're trying to place a bet, and we get a whole bunch of event notification of of domain events. They are slightly split to make them more suitable for user interface, but still they contain all the same information, just maybe in two separate messages instead of one. So what we can see here, let me. So the first notification corresponds to bets accepted event. We have the amount of bet and the alternative. We update in the current status. Game goes to collecting. And the thing is that the game actually came across all these transformations but everything was fine. Game never stopped. And you haven't actually seen this transformation, you only see the eventual result. Game ended up in the finish state, but still all these notifications have been received and game have processed those. So we have update of the balance. We have lost, so the resultant balance was 9. The outcome loss, because winning option was tail. And finally, we switch to this finish state where we are at the moment, the last update. Now let's try to add even more details to our picture. And let's think how would we like the error cases would be handled in case if there is something wrong with the wallet. So let's focus mainly on we will handle separately HTTP codes for server errors and client errors. And even experienced developers from time to time confuse those. The HTTP protocol provides us quite clear guarantees that in case of 400 error, you can expect that your request was rejected and you don't have side effects on the processing system. And you can safely get back to the bets awaiting. You have guarantees that nothing was withdrawn from the player's balance. On contrary, in case of 500 error, it can be, for example, null pointer exception at the very end of the processing, for example, during the final serializing, but the request itself could have been processed. So we have to try again until we get some clear result. And this is exactly the case for when we have to provide player information that we're trying to process the request again and again. It is all the same with the HTTP with the win processing, except for there is no reasonable way to reject player's win. If he got this win, he will need eventually get it. So there is no way for us to return to some other place. We have to retry again and again, even in case of client-side error. So let's try to see how it works in the code base. So we have all the events, all the domain events implemented as case classes, all the events that we have discussed, and they have only the information that relates to this particular event. So we don't want to overload the event with extra information that is not needed for the state updating. And the state itself can also be modeled as a case class. That's the main reason why we ended up using we're trying to do as much as possible as a plain Scala code, and we're trying to avoid binding to technologies, even good technologies like persistent finite state machines, but we prefer to use it in a plain way. What we have in the state of the game is exactly all the fields that we have on the user interface: round ID, current status, the bet, which is only available after bet accepted event, and the result, which only available in payout and finish states. So these are options. And the status is the one of these. These are the 5 main statuses that we have seen on the diagram: awaiting, collecting, calculating, paying out, and finished. HTTP versus WebSocket. Well, you can see that actually all asynchronous reactive systems, they have natural forces that drive towards naturally asynchronous protocols. So, well, we did started to try to use HTTP with Akka to respond to user interfaces, but indeed, in Akka world, turned out for us surprising that it requires even more efforts to handle it via more simple protocol like HTTP. So you have 2 options: either you can embrace the fact that WebSocket is more suitable for reactive systems, or you can do it wrong like we did and try to somehow collect the events until the opportune moment when you can send them back to the user interface, which will take you some extra efforts. So the last step would be to assemble it all together. The way how Play Framework handles WebSockets is that it have controller that spawns WebSocket connection as a separate actor. And one more thing that we haven't talked about yet is that we don't want a multiple instances of a game for one player to be run simultaneously at a time. In case if player have several connections from different devices or from different browsers on the same PC. So we need to have some kind of manager that will handle this. Namely, it have to forward the connections to one single instance of a game for a player. And we have already seen this part, the flip state and its internals. We have a reference to the client connection via WebSocket, and this part, the events, that's what we need in order to restore the game state back to the point where we have left it when we close the browser or the browser have crashed or whatever. And the last part is the wallet actor, which simulates communication to wallet, which as you will be able to see in the source code, is just a bare implementation with some simulation of errors. And finally, we get back to the present days of the evolution, and the story goes as we speak. We started to use CQRS for other services and products. We still have to go to production with cluster and Akka sharding. Maybe it can be a topic for next year. So Thanks everybody for your attention. We can now proceed with the questions.
Thank you very much for the talk. Just out of curiosity, could you estimate how many event types did you had for your flip coin example? Like, yeah, different event types. It's like 3 dozens of them. So 1 dozen now, around 2 dozens. And on another screen, those weren't events? But they kind of extend flip event still. So from the system perspective, they're still events. So I guess they count in. Okay. And on another screen, there's weren't events. There's just internal representation. Okay. Thank you.
Out of topic, which tool you use for monitor actors?
Sorry. Well, we currently not using any particular tools. We just arrange in our internal actors that are handling the life cycle of the game actors inside us, but we don't use any particular third-party tools for that.
For all application.
Okay. For example, maybe you will give an example so that I understand more the question. Monitoring yeah, I see. Well, we only trying to adopt Grafana, but it's not on production environments, so we're doing kind of manually.
As I understand, you don't use Akka cluster and Akka persistent.
We use an Akka persistence, but we haven't adopted cluster only for prototypes, not for production environments.
And what do you do if you need to change event structure?
For now, we just doing custom JSON serializers. We keeping the version in the manifest and having several versions of the serializers that backward compatible. For the 1 year of history, we actually experienced only backward compatible changes. There were no crucial changes that would need complete refactoring of the events. And we have the backdoor. We can just reissue the game as a new brand. So it is easy for us to get rid of this problem naturally.
Okay, thanks.
Why have you stick it to Tomcat and Play framework? Akka HTTP looks like more natural choice for that.
No. Play framework was on the slide with dinosaurs. It was long ago, not anymore. It's just plain Play framework with Akka HTTP, of course. Yes. Okay. Thank you so much for your attention. Special credits to my whole team that shared brilliant ideas for this presentation. Thank you so much.